Hello and welcome to this video. So we are going to be getting into section 2.4, which is scatter plots, correlation, and regression. So this is a new topic that was not included in the lecture notes, so make sure you find those lecture notes in the video links folder, so that way you can follow along. All right, so what this section is going to do, it's going to provide an introduction to how paired sample data can be analyzed. So again, you're looking at two numbers that are going to be linked together, and you're going to have a bunch of sample data formed that way. So in order to do this, though, we're going to first need to know what the term correlation means, and also how a scatter plot is going to actually help us to be able to do that. So let's start with that. And we have a few definitions to get through first. So the first one being a correlation, which exists between two variables, two numbers, when the value of one variable are somehow associated with the values of the other variable. Now, we can get into more specific relationships if we look at the next one, which is a linear correlation, and that exists between two variables when there's a correlation. So again, there's a linkage, and the plotted points of paired data result in a pattern that can be approximated by a straight line. So, there's going to be a visual aspect to this exercise, and that's where the scatter plot comes in. So a scatter plot or a scatter diagram is a plot of paired data of the form x, y, so it's an ordered pair, it has parentheses around it, with a horizontal x-axis and a vertical y-axis. Now you might remember that from your days in high school, but if not, we're going to get right into it. So the horizontal axis is typically used for the x variable, and the vertical axis is used for the second one, which is the y variable. Now, a couple of things to be careful about. If it is determined that a correlation exists between two variables, it does not mean that one variable causes the other variable. So very important. So in general, correlation does not imply causality. That's the nice compact way to say that if two things are linked, if two variables are linked together or correlated, as you can see down here, this does not mean that one causes the other one to happen. So very important. And just to give you an example of that, we can look at smoking and lung cancer. Now, many people would say, well, smoking is probably the #1 leading cause of lung cancer. But that is not 100% true. And that's the catch in all of this. So even though there's evidence to support there's a linkage between those two things, you cannot definitively say that 100% of the time smoking is going to cause lung cancer. There's exceptions to that. If you want to research it yourself, go look up George Burns. George Burns was a comedian. He lived to be over 100 years old, and he smoked cigars his whole life and never got lung cancer. So, and there's multiple examples if you want to look. So again, correlation does not imply causality. Very important. All right, so let's take a look at an example. So this first example here is looking at overhead body widths of seals in centimeters collected from aerial photography and the weights of these same seals plotted in the accompanying scatter plot. So you can see those numbers there and their corresponding weights, and they're all plotted in this scatter plot. So one of the things you can see by this is that there's kind of a general shape going on with the way the data is laid out. So, and if you wanted to kind of explore that, you could say, oh, well, what if I put a line in here? So if you put a line in here somewhere, it kind of follows that line. It's not too far away from that line. Now, you might be able to adjust it a little bit to get it even better, but the point is that it does follow a linear path. So as you're going from left to right, it's going uphill. So now, what we can go and say from that is that there appears to be a correlation between the overhead width and the body weights of seals. More specifically, there appears to be a positive linear correlation between the two variables. This terminology will explain more in detail shortly. So, okay, so we're kind of looking at visuals to see if there's some sort of relationship. So let's see how we can do that with a new set of data. So you can see we have forecasts and actual temperatures here. So the table below lists the actual high temperatures and the high temperatures that were previously forecasted for these same days. The table includes data for 10 different days in the semester. What does the results suggest about the accuracy of 5-day predicted high temperatures? So we're going to have to plot this information out in a graph, which can be a little bit of a pain if you're trying to do it by hand. But we have technology that can help us. So what I'm going to do is I'm going to open up an Excel spreadsheet. So we'll let that open up. And we'll just pick a blank one. And we'll make it a little bit bigger here. So we can easily cut and paste this table into Excel. So we can just right click, highlight it all, right click it, and then hit copy. And then we'll switch back to the Excel spreadsheet. And we can right click in that first cell and just hit paste. And there's our data. Now, if we want to put this into a scatter plot, again, very easy. It's already highlighted. So if we go up to insert, we can look over here and see all these different charts and things like that. But if you kind of mouse around, you can see that some of these have names to them. But this one right here says insert a scatter or a bubble chart. And that's what we want. So once you click on it, once you left click on it, it's going to give you some options. But let's just pick that first one. And that gives us our scatter plot. Nice and quick. And if we want to put it back into our notes, you can do the same thing. You can copy it, and then we'll switch back to our notes, and then we'll right click again, and we'll paste it. And there it is. Now, what's a little bit clunky about this is that it does kind of push things across onto the next page, but we can fix that by just changing the wrapping. So if we wrap it, I'm going to put it in front, and that will put it there. All right, so what does the results suggest about the accuracy of 5-day predicted high temperatures? Well, is there a relationship? Remember, that's what we're looking for. Is there a relationship between the data? Does it form some kind of line? And the problem with this one is that it's kind of all over the place. You might say, well, I could probably put a line in here. Maybe I could put a line, something like that. But again, you've got problems with some of these data that are really far away from that line. So no matter how you laid it out, it's not going to give you a good representation of the data. So in this case, since no line can describe the data accurately, there does not exist a correlation. Done. And that's going to happen sometimes. Now, again, this is all a visual, guess about what you think it's showing you. We're going to get to more mathy type of ways to describe or to confirm that if there's not or there is a correlation. But let's take a look at one more example. You can see this one. This one's right from the textbook, page 75. And you can see we have clumps of data in 2 different spots. And this is called like a gap scenario. So the technical wording is in the textbook, but we're not going to get into this type of scenario. So I wouldn't get too nervous about it. But this one, again, it's hard to really say that there's a line that describes that. You might say there's a vertical line, somewhere in here. But yeah, you really can't say much about this one aside from it being a gap situation. Okay, so that's one way we can look at data, just by looking at the graph and kind of making a guess about what we see. But there are better ways. So we're going to look at part 2, which is the linear correlation coefficient R. So although we can visually determine whether there is a potential linear correlation between 2 variables based on a scatter plot, this can be subjective and depends on the viewer. Instead, we should identify or calculate a linear correlation coefficient that will help determine if linear correlations exist more definitively. So what is this linear correlation coefficient? And it's going to be denoted by the variable r. And what it does is that it measures the strength of the linear association between two variables. So the strength, how strong is there a linear correlation? Now, we're going to see there's some limitations to that, but let's just read on. The value of the linear correlation coefficient R can be manually computed by applying formulas found in 10.1, which is way farther in the book than we're ever going to get. But in practice, R is almost always found by using statistics software or a suitable calculator. As such, we will not be calculating the value of R in this section, but we'll be provided it for analysis purposes. So it's going to give it to you. So you don't have to worry about trying to find it or calculate it any particular way. So what are the restrictions for it? In general, R is restricted to be between -1 and +1. So we can write that as an inequality. -1 is less than or equal to R is less than or equal to 1. So in this sense, we have the following. 3 scenarios. If R is close to -1, then there exists a negative linear correlation. If it's close to +1, then there's a positive linear correlation. And then the third case, if R is close to 0, then there's no correlation between the two variables. So let's put that back on the previous problems. For example, the scatter plot of overhead widths and weights of seals has a calculated value of R equal to 0.948. So that's pretty close to +1. So that does support our assumption that there was a positive linear correlation for that data. Now, the problem with this is the phrasing close to. Well, what does close to mean to you? It might mean something different than what it means to me. So we need to be a little bit more detailed, in which we're going to get to as we go. So one of the things that's out there is a table that's going to identify some more specific cutoffs for that close to definition. And it's all dependent upon the number of pairs of data that you're dealing with. So this table goes from 4 points all the way up to 12 points. And then we have the corresponding critical value of R, which we're going to see how to use that in just a second. But before we do, the one thing to keep in mind is that critical values include both the positive and the negative values. So don't just assume it's a positive number and that's it. So for this case, we need the positive and the negative critical values. So one of the examples we can look at is for n equal to 5. So we had 5 data points. And so going back up to the table here, we can see there's that critical value of 0.878. So in this case, if n is equal to 5, then R is equal to 0.878 and negative 0.878. So we need both of those. And we can combine them into one compact statement by saying R equals plus or minus 0.878. Now, so what does this all mean? Well, remember, each data set is going to have its own unique R value that's pre-calculated. So for these 5 values, let's suppose that R was equal to 0.591. So what does this all mean? Let's put it all together now. So looking at this diagram here, we can see that, okay, we have R that's stuck at -1 here, +1 on the right side, and then we've got those critical values that are identified in here, and then the R in question, 0.591, which we can see is in the middle. And because it's in the middle, that means there's no correlation in this case. So essentially, you're looking at 3 buckets determined by those critical values. You have your left-hand bucket that's close to -1, you have your right-hand bucket that's close to +1, and then you have the big bucket in the middle where there's no correlation. So again, because R is in between those 2 critical values, that means there's no correlation. Now, what if we had a different data set with 5 pairs of data and the R value was going to be negative 0.912? Well, we're doing the same thing. Where does negative 0.912 fall in our diagram up here? Negative 0.912 is going to fall right in this left-hand bucket. It's between -1 and negative 0.87. So because it's in that left-hand bucket, close to -1, Now you could write this a few different ways. If you wanted to write it as an inequality, you could. And then make sure I put my negatives in here. So that would show us that there's a negative linear correlation in this case, because again, it's in that far left-hand bucket. So let's try a whole new example and see what we get. So the linear correlation coefficient R is provided. Use table 211 to find the critical values of R. Based on a comparison of the linear correlation coefficient R and the critical values, what do you conclude about a linear correlation? So using the data from example 1, forecast and actual temperatures, the linear correlation coefficient is R equals negative 0.475. So remember our graph from up above, our scatter plot. So remember, we kind of thought there might be something negative, and there kind of is a little bit of a negative trend, but can you put it on a strong, solid negative line? And the answer is no, and the value of R justifies it. But let's go through all the hoops. So the first part of the question says, what are those critical values? So how do we determine that? Well, remember, the critical values are based on how many data points you're dealing with. So let's go back up again. So we had how many data points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 points in our example. So if we go back down to table 211 and look at 10, so our critical value is 0.632. Now don't forget the negative though. Okay, so that's the first part. We have the critical values. And now we have to compare our R value to those critical values. So remember, those critical values form your three buckets. -1 to the first negative critical value, and then you have between the two critical values, and then you have the positive side. And if we look, we can see that this R value is between those two. And remember what we said, if it's between, then that means there's no correlation. So that's what we get here. I'm having a hard time typing, so bear with me. So again, in this case, because it's in that middle bucket, it's between those critical values, then there does not exist a correlation in this case. All right, so we have our scatter plots. That gives us a visual. We have our R values. That's a little bit more specific. Now it determines three buckets. That determines if there's correlation or not. And then there's a third check that we can look at, which is looking at the p-values. P-values for determining linear correlation. So while knowing the value of the linear correlation coefficient R is valuable for determining whether or not a linear correlation exists, there's another check that can be used to further determine the probability of getting a specific value of R or larger. So definition, if there really is no linear correlation between two variables, the p-value is the probability of getting paired sample data with a linear correlation coefficient R that is at least as extreme as the one obtained from the paired sample data. Now you're probably reading that saying, what in God's green earth does that mean? Let's break it down. What this means is only a small p-value such as 0.05 or less, and 0.05 you should know is 5%, so it's 5% chance or less, suggests that the sample results are not likely to occur by chance, when there's no linear correlation. So a small p-value supports the conclusion that there is a linear correlation between the two variables. Okay, now you're probably saying that still doesn't explain it. Keep going. Well, let's look at an example. So this example is looking at shoe print lengths and heights of males. So we have those paired data. There's 5 pieces of data, and they're plotted in the scatter plot. All right, it has a little bit of a uphill, well, if I go the other way, an uphill climb from left to right. So it seems like there might be some positive going on there, but let's look at the numbers. So our correlation coefficient are 0.59127. Now, obviously, technology can get more detailed R values, but we're only going to be looking at 3 decimal places. Here, they're looking at 5. So that's the R value. So not super leaning one way or the other. It's positive, but it's not super close to +1. And again, our critical R values are plus or minus 0.87834. But now look at the p-value, 0.29369. All right, let's put it all together now. So we have our R value of 0.591. The critical values are plus or minus 0.878, which supports no linear correlation. So again, R is between those critical values again. If it's in that middle bucket, there's no correlation. But even further, the p-value is 0.294, which is much bigger than 0.05. Remember what we said up here. A small p-value means that there is a linear correlation. So because the p-value is too big, it's bigger than 5%, then it's no good. It also shows that there's no correlation. Let's do a slight tweak to this problem. What if we increase the sample size a little bit? So look at our scatter plot now. Now it's a little bit more looking like there's a linear, wrong way, a linear correlation, a positive linear correlation. So if we look at the values now, the Pearson correlation of the shoe print and height equals 0.813. So again, that's the R value. Again, it's close to +1, but is it super close? Not according to the critical values, but remember, the critical values are dependent upon the number of data points. And we don't have, this has got a lot of data points, and we don't have those critical values. But look at the p-value. P-value is equal to 0.000, which is really, really small. So with this larger sample, we see that R is equal to 0.813, and since the p-value is 0.0000, which is less than 0.05, this now suggests that there is a linear correlation between the two variables. So even though the R might not fully support a linear correlation, again, because you might have too many data points and you don't know those critical values, the p-value will strongly determine that. So sample size matters. So be careful of that. All right, let's try one more example. Write a statement that interprets the p-value and includes a conclusion about linear correlation. So again, using the data from example 1, forecast and actual temperatures, the p-value is 0.166. Okay, so remember, p-values, you're always comparing it to 0.05. So how does that compare to 0.05? It's bigger, right? So because it's bigger than it, then that means there's no correlation. And that's it. So what are we taking away from this? So number one, you should be able to view a scatter plot to get an initial interpretation if there's a linear, a positive linear, a negative linear, or no correlation exists. Again, just a visual look to say, okay, what does it look like it's doing? Then you start getting into the details. You should be able to use the given linear correlation coefficient R and table 211 to determine if sample data yields a linear correlation or not. And then the third check, using the p-values. You should be able to use the given p-values for sample data to determine if a linear correlation exists or not. So that's all you're really going to need for this section. Now, the final part of the section, which we're not going to cover, is regression. Which I don't know why it's not there, but it was before. Unfortunately, we're not going to be doing regression, but regression is essentially looking at, we think there's a line there, but what's the equation of the line? So that's what regression is finding that equation of the line. We're not going to do that, even though it's kind of cool, but you can do that in other statistics courses after you take this one. But that covers this section, so I hope you have a better understanding of it. But if not, please feel free to contact me. Alrighty, take care.